Hello physicists. In this video, we're going to be talking about changing velocity. Okay, so last video we talked about the instantaneous velocity, and we were able to find the rate at which the position changed. So now at this point, we can do calculations, we can perform calculations with constant velocities pretty consistently. However, in real life, constant velocities don't really exist completely. Velocities will change at some point, either when you start moving something or when an object is slowing down. So when velocity is changing, we need to account for that change. And that change is called the acceleration. And the average acceleration is defined as the change in the velocity over the change in time. So it's the difference between the velocity vectors over the length of the time interval. So it's the change in velocity over the change in time. And if I were to look at a velocity versus time graph, the average acceleration between points A at time t0 and time n at point B at point tf this is v0 and this is vn. So if the average acceleration is equal to the change in velocity or the change in time, that's just the slope of the graph, okay? That's just the difference in the y values in this graph over the difference in the x values, which is the time. So we get the acceleration to be equal to the slope, similar to how velocity was the slope of a position versus time graph. How velocity was similar in a position versus time graph. Now, acceleration can be positive or negative, just like velocity. So velocity, as you might recall, we define velocity as positive if it's moving to the right. So velocity is in the positive direction. And if it's going in the negative direction, so leftward or downward, oh no, the F doesn't matter, then the x component, the component of the velocity, the x component will be less than 0. It will be negative. The speed will be negative at that point. Now, we can introduce a similar concept for acceleration. Now, acceleration is the rate at which velocity changes. So if the velocity becomes more and more positive, okay, so let's get some more space. And let's rewrite our average acceleration equation. Okay, so if we have a car and it's traveling at some initial velocity v0, and we make it faster, that means if it's speeding up, then its final velocity vector, VF, will be in the same direction, but a lot longer because we've just increased its magnitude. It's speeding up. So the difference VF minus V naught will be pointing to the right. And because we're dividing by a scalar, the acceleration has to be to the right. Because time is always positive, so it preserves direction. So when you're speeding up in a particular direction, then the acceleration will also point in that direction. In other words, if you're speeding up, then the velocity and the acceleration vectors will point in the same direction. Now, what happens if our car was moving to the right but starts slowing down? Well, intuitively, you might think that the acceleration will be negative. Okay, and we can show that. We can show that the change in the velocity, that vector, is pointing to the left. And because time's positive, we have the acceleration pointing to the left as well. So if a car is moving to the right, the acceleration sort of tugs on the car, it's pulling on it, trying to make it stop. And eventually, when it does stop, and the acceleration continues, then it will start heading toward the left. So what you can interpret this as is that the acceleration increases the velocity vector's magnitude in the direction it's pointing. So if acceleration's pointing in a negative direction, then the velocity vector will become more and more negative. So if it starts very positive, then it'll go closer to zero because that's how it become more and more negative. And then it will point in the opposite direction. So a car would be moving to the right, and then it will stop for a moment and then go straight to the left. So that is the concept of average acceleration. So let's just apply some numbers. So imagine you had a car, and your car had an initial velocity of 30 meters per second. So it's a pretty fast car, and you decide to brake until it comes to a speed of 15 meters per second. And all of that happens in a time interval of a minute. So what is the average acceleration of our car? Now, the average acceleration, we can use the vector notation, or we can just use the scalar notation. Vector notation is more useful because then we get to mathematically describe the direction. So that's what I'll use here. So it's the change in the velocity vectors. Now the first velocity vector is pointing in the I direction. The I direction is defined to be rightward, positive. So the I direction is rightward. That means our initial velocity was 30 meters per second in the I direction. So it's 30 meters per second in the I direction. that's our initial, so... Oh dear, okay. Our final is 15 meters per second in the I direction, minus our initial, 30 meters per second in the I direction. Notice how, because both of these are rightward, we use positives. But watch what happens. 1 minute. 1 minute is 60 seconds. You have to use seconds for these problems, SI units. So you have 15 minus 30. That's... Oh. You have 15 minus 30. That's negative 15 meters per second in the I direction over 60 seconds. And that is equal to negative 0.25 meters per second squared in the I direction. So, did you see how all the numbers automatically adjusted? It's because we use the vector notation. We use the I notation. So now we know the exact direction. It's the magnitude is 0.25 meters per second squared, and it is pointed leftward since it's negative and negative of the I direction. Thanks for watching. See you next time.